Electrochemistry. Electrochemistry really falls into a different class of reactions. It's a class of reactions that involve what drives it are the transfer of electrons between reactants. And one set of reactants is actually producing electrons. The other reactant is actually, collecting them, reacting with them. And sometimes it happens spontaneously, sometimes it doesn't. But the electrochemical reactions that happen on their own spontaneously, those are the important ones. Those are the ones that, interact here. It seems odd. We're going to talk about cells, and how these reactions, well, all these reactions are in one big mess, one big glop inside here. But one set of reactions produces electrons, the other set actually reacts with them. And you can kind of see the guts inside of a battery, or the reactions themselves. Okay. Aluminum cans. It takes a lot of electricity to produce aluminum, and even 6 kilowatt hours just for 1 pound. So that's why this recycling is a big deal. Right? It's a lot to get the aluminum from cans that are already pure aluminum. There's a lot of electrochemistry in sensing. If you're ever gonna, get married or something, and you got to have all the fruit out on the plate, stuff turns brown. But if you dip the knife in what first, it's going to stop that electrochemical reaction in lemon juice. All right? It's kind of interesting. So electrochemistry is pretty useful. Here's one electrochemical reaction. They use it to join railroad tracks, and it's called a thermite reaction. So it must be pretty powerful.
Aluminum metal is a very strong reducing agent. The flower pot contains thermite, a mixture of finely ground aluminum metal and iron-free oxide, plus a starter mixture containing magnesium metal. The reaction is initiated by igniting the magnesium metal ribbon. Some of the molten iron has flowed out through the bottom of the flower pot into the bucket of sand.
To me, that's just crazy. I mean, you have a mixture of a couple reactants, a couple metal powders, and you can actually melt iron. But again, we're going to talk about these electrochemical reactions that are all in one big pot there. You really didn't see one reaction physically divvied up from the other reaction in cells, but that's what we're really going to get at. Here's the reaction, the thermite reaction. See if we can review some terminology. One, oxidize in a reaction. Oxidation state gets, do you remember? It gets more, you remember? Okay, you got two things going here. Good. You're thinking about it's losing these electrons. Yes. So that means it gets more positive. Right. It gets more positive because it's producing all. Exactly. Yeah. So it's kind of contradictory in nature there. But, so it itself gets more positive, losing these electrons. It's producing them. When an element gets reduced in a reaction, its oxidation state gets more negative, right? It's actually reacting with the electrons. So this whole electrochemistry and this whole idea of oxidation states is really just to keep track of these electrons. Do bookkeeping, right? You're going to react with 3 electrons, well, you better produce 3 electrons, that kind of thing. Oxidizing agents and reducing agents, what destiny? Reactants or products. They're the agents. They're the cause for the change. I don't know if that's much of a hint, but they're the reactants, always. Okay. See if you remember that. Javier, Oxidizing agents always get reduced. Yeah, that's how I remembered it, right? Oxidizing agents always get reduced, always reactive. Reducing agents, everybody always get oxidized. Oxidized. They're always reactive. Okay, let's see if we can figure out what the oxidizing agent, reducing agent is in this above reaction. Although the reducing agent. Now, the reducing agent has to have gotten, it has to be a reactant, and it has to get oxidized. Okay, so Fe2O3, I mean, you can fix an iron, but aluminum is just sitting there all by itself. If you remember the rules, you can look at aluminum, and you know exactly what its oxidation state is. Now, I hear +3. Aluminum does cation +3, but that's not what's written. If it oxidation state of aluminum would be +3 because it's just the charge on whatever it's there. What's the charge on this aluminum solid? Nothing's written, so the charge is 0, right? So that means this guy, his oxidation state is 0. Now we have to figure out what aluminum is on the product side. Let's see if the number got Shelby. We want to figure out what aluminum is over here. The only way to do that is if you remember what the rule is for oxygen. If oxygen in a compound, its oxidation state is always -2. Good. Okay. It's -2. Now, the overall charge on this aluminum Al2O3 compound, everybody, is 0. So I've got 3 oxygen atoms and 2 aluminums. I've got 5 atoms total. Add up the oxidation states of all of them, they better add up to be 0. Alone, I have a -6, right? Because I have 3 of them. Each one's -2. So the aluminum has to be total a +6. So each aluminum must therefore be +3. Get rid of the question mark. +3. So that means that aluminum solid, Jasmine, it got oxidized. So that aluminum solid must be the reducing agent. That's got to go over here. That means the other one, you can figure it out if you want. But the other reactant has to be the oxidizing agent. Okay, it has to be. That iron must have got reduced. Write the unbalanced half reaction. So we don't want to balance them. Just want to identify what the half reactions are. Adrian, you remember how do you do this?
2Al.
Yeah, aluminum goes to aluminum oxide, Al2O3. Now they wanted 2s and balancing all this stuff. Aluminum goes to Al2O3. The other half reaction must be the iron oxide. Whoa. Yeah. There's the 2 half reactions. Now they're not balanced, but not just balanced. Okay. So you can actually, even though you have this one big clay pot, you can look at the chemistry of it and say, okay, well I know it's a big, powerful reaction overall, but something is producing electrons, something is reacting with them, and it's happening very violently, right? So you can divvy them up and understand more what's going on. So when you can divvy up for this chemical process into something's producing electrons, something's reacting with them, right? It's kind of confusing to me because they like to use the word cell. Well, cells to me means you have one reaction going on over here and one reaction going on over here. And you can't have it go that way or just have it all in the same big clay pot. Okay, so we're talking about these electrochemical reactions, and they're going to call them cells. And these electrochemical reactions can either be non-galvanic or galvanic. 2 categories. Let's take a look at the non-galvanic category of electrochemical reactions. A pickle light.
A pickle is incorporated into a simple electrical circuit. The forks provide contact between the pickle and the power source. Alternating current will be passed through the circuit.
Okay, so inside that pickle, something was reacting with electrons and something was producing them, Ray. Did it happen spontaneously? Or did you have to force that to happen? You had to force it. They had to plug the dang thing into the wall or some big power supply, right? So that's called a non-galvanic cell, right? Getting those aluminum cans from alumina, from these ores, that's non-galvanic. You have to kick in a lot of electricity to get it. It's expensive. So that's one category. The other category is galvanic cells. And here's a galvanic cell.
This lemon battery is related to the zinc-copper cell. You can build this battery from lemons, galvanized nails, and pennies. How much electrical potential is generated by a 3-lemon battery?
About 1.5 volts, it looks like, right? So if they would have used more lemons, made more batteries, Matthew, what do you think is going to happen to that voltage meter? It'd be higher, right? Over time, let this thing sit there for a while, well, what's going to happen to that voltage? It's going to go down. Why? You know it has to, because things don't last forever, right? Batteries, their voltage goes down over time. Why?
Whatever reaction is being used.
Exactly. Whatever reaction's going on, that stuff's getting used up inside those lemon batteries. Yeah, stuff's getting used up. Those are reactants. And it looks odd. Again, where are the two reactions? Well, they're all in there. Something in there is producing electrons, something in there is reacting with them. But it's happening spontaneously, so they call it a galvanic cell. Okay. Which I think is the category which is, much more heavily studied spontaneously. All your sensors and all those types of processes. Batteries. Okay. What are the half reactions in the lemon battery? So I got to tell you those. Now they said they had galvanized nails or galvanized screws. Galvanized just sounds a lot better than zinc coated because it's going to sell, I guess. But that's one of the half reactions, is that zinc is actually going to zinc plus 2. So you have the cheapest metal is iron, but it rusts. So you galvanize it. You just coat it in zinc. Okay? So the zinc will react before the iron will. And once all the zinc goes to zinc plus 2, then you're going to start rusting. Okay? Yeah, it's still through my little F. Okay, so there's one half reaction. Oh, it's not balanced, though. Mariella, how do I balance that half reaction? The zincs are good, but the charge is messed up. Add 2 electrons to the reactants or product? To the product. Remember that last step was add electrons to the most positive side. Okay, so there's one half reaction. The other half reaction is they jam some pennies in the lemon. And this is why you need a lot of lemons and to get things going, because it's copper plus 2. You jam a penny into a lemon, right? The copper penny, that's solid. It's not reacting. The copper penny has to a little bit, right? And then it it reacts. It goes to copper solid. So that's why the whole thing doesn't really happen. Whoop. Yeah, copper solid. There's some copper in that lemon too. So now to do the balanced half reaction, put two E minuses over there. Okay. So this is all inside of the lemon battery, but you can divvy it up into an electron in a reaction that produces electrons. The other reaction reacts with those electrons. Okay. So if you separate these two half reactions into actually different cells, different containers, what would it look like?
A galvanic cell consists of two half reactions connected by a salt bridge and an external wire. In this example, a zinc metal electrode is oxidized to zinc ions at the anode, and Cu2 positive is reduced to form copper metal at the cathode. If the two half reactions are connected through a voltmeter, we can measure the electromotive force for the reaction. When connected to a light bulb, the current of electrons flowing through the wire causes the bulb to glow. The anions and cations flow through the salt bridge to compensate for the change in the charge caused by the electron flow.
Okay, now we back up a little bit here. Where are the galvanic screws at? This is supposed to be modeling a lemon battery. Where are the galvanic screws? It's the zinc. Here they don't have a. They could have put a screw in there, but they just have a whole hunk of zinc. A zinc strip, a zinc piece of metal. The copper pennies, they're going to be the copper. And notice how they have both reactants and products there. You've got the zinc metal, you've got the zinc plus 2 here. You've got the copper metal and the copper plus 2. They're both there. They're just in different containers. And then you got this wire connecting them so electrons can flow. So everything looks like it's there, except you have this funky salt bridge in there. What is the purpose of it? Allows flow. Could I pull out the salt bridge and just stick my finger in one, my other finger in the other one?
Without a salt bridge, you know.
The answer to these questions really. To answer these questions, you pretty much almost had to have played around with. Did you ever have a battery light bulb? You had to play around with getting the light bulb to light. Mm-hmm. Okay. If you disconnected, so you got the light bulb to light. You disconnected any wire anywhere, what happened to the light bulb? It turns off. So that's one thing about electricity. You had to have a complete. It was a big word. Now, in other words, you had to have current flowing. What's going on inside this electrochemical cells, you got to realize you don't have to have electrons flowing through a wire to have current. Current is any charged particle moving. So you get Na plus. If it's just sitting there, you don't have current. But if that Na plus is moving, I have current. Cl minus, it's charged, it's moving. That's current too. So in this salt bridge, you have is moving. So there's my current. I'm circuit. I could pop that salt bridge out, stick one finger in one, stick one finger in the other, and it's why? Because I've got ions inside myself, and they're going to move. I have current. Current will pass through me. I'm not an insulator. Right? Drop a hair dryer in the bathtub, and you'll find out that you conduct electricity just like water does, and you boil up. Now, the voltmeter here reads 1.1 volts. When they did the lemon batteries, it was 1.5. Why are they different? Same reactions. Ooh, the amount. You could have a number of different lemon batteries. Exactly. The concentrations of the zinc and the copper solutions could be different. Right? So there's a lot of parameters. Let's see. Okay. So we want to be drawing these things. There's going to be a long way and a short way to describe these cells. By convention, the oxidation half-reaction, it always occurs in the left cell. Okay, that's just what we want to remember. And that means that electrons are going to flow from left to right or right to left. Oxidation half reaction. Which one of these is the oxidation half reaction? The top one or the bottom one? Oxidation gets more positive. So it has to be the top one, right? Because zinc is from 0 to +2. So oxidation half reactions produce electrons or react with them? Electrons are an oxidation half reaction. Electrons are a product or a reactant. They're a product. They're being produced. So electrons are being produced. So when you draw these guys by convention, right, over here, they're supposed to be producing electrons. So that means they're going to go from left to right. Okay. You always draw the oxidation half reaction in the left-hand cell. Now the reason for that is so you know how to hook up the voltmeter. If you hook up a voltmeter across this battery, you'd read 1.5 volts. But to do it right, you're supposed to pick the red one to the positive and then black one to the negative, and you read 1.5 volts. What would happen if I switched the probes around? The red to the negative end and the black to the positive end. Well, I'm just reading the voltage on here. You ever try it? All that you still get 1.5 volts. You just get negative 1.5 volts. It's just the sign just changes on you. If you have a flashlight, yeah, okay. Well, we'll get into that later. Let's see. Okay, we're trying to draw conventional voltaic cell diagrams. So you have to do something like this. Draw a couple beakers or cells. And on the left-hand side, the left cell had better be the oxidation half reaction. So the right-hand one must be the other one. So pretty much, draw your hunk of metal. And on the left-hand side has to be the zinc. So there's my zinc solid. Supposed to be zinc solid. And I need zinc +2 in solution. So maybe draw a little wavy line for solution or something. Okay. And on the right-hand side, I'm supposed to have copper. Little wavy lines for some copper +2. Right. Sometimes they draw a V. Probably for what? Volts for voltmeter, right? Something measuring the voltage. So they draw a little light bulb or something. And I got to complete the circuit with a what bridge? Salt bridge. Okay. And there's one other component. The direction of electron flow, and it was always from left to right. They're getting produced over here, so they're going that way. Okay. I don't think they really care if you label the anode and the cathode, but we should probably know which is which. Which one's the anode? The zinc. Why? Yeah. However, there's a number of ways to remember this. Oxidize. That's the only way I remember this. Is anode and oxidation both start with a vowel. That's the only way I remember this. So you can remember it how you'd like, but the anode is oxidation's always the oxidation occurs. This must be the cathode. Okay. But it's a lot easier, I think, to do this shorthand notation. And in the shorthand notation, does anyone know what you draw for the salt bridge? Lines. There you go. There's my salt bridge. And then the rest of it, pretty much you just look at the half reaction. And I have zinc solid going to zinc +2. Right? That's has to be on the left-hand side. I have zinc solid going to zinc +2. But I don't draw an arrow. Whoop, zinc +2. Instead, I'm either going to draw a vertical line or a comma. In this case, I have to draw a vertical line. Does anybody know why? No. The reactants and the products in this half reaction are in different states. There it is. They're in different states. One is a solid, the other one is aqueous. It doesn't always have to be that way. They could both be reacting in solution in one big mess. You could dump all this stuff in the same beaker, right? Now, this reaction progress, but you wouldn't have the electrons flowing through a wire then. But okay, they have a comma, and if I know the concentration of the zinc plus 2 solution, I would write it in right here. If I knew it was 0.2 molar, I'd put it in there. So now on the cathode, I have copper plus 2 going to copper solid. So you just write in copper plus 2, and the concentration if I knew it, but I don't. Vertical line, because they're in different states. It's a lot easier. Right? A lot easier. Yeah, we should. But remember, I've been lazy from day one. Whenever you write a cation or anion, right, it has to be aqueous. Otherwise, it won't be dissolved in water. Otherwise, you can't have a cation or anion. You've been leaving them off. Iron reacts spontaneously with copper 2. Obtain the half reactions, then describe a voltaic cell using these half reactions. Okay, so first let's get the half reaction. And then we'll do the shorthand notation. Alexa, what would be one of the half reactions? Iron solid going to iron plus 2. Okay. And then you can wrap it up by balancing the charge. Yeah, perfect. Add 2 electrons, you said, to the most positive side. All right? And then we need the other half reaction. Lewis, what would the other half reaction be? Yeah. Yeah, and then we got to balance the charge. Yeah. No. You could have 2E minus plus copper plus 2 or copper plus 2. A plus B is B plus A. They're the same thing. Okay, there's our 2 half reactions. Now they want us to describe a voltaic cell. You could, since they didn't specify, you could draw the whole thing out like we just did. The conventional voltaic cell diagram. I say you just do the shorthand notation. Right? Do the shorthand notation one. It's a lot easier. If they didn't specify. You got to figure out, though, the right one to put on the left-hand side. That's got to be the oxidation half reaction. Make sure you put the oxidation half reaction on the left-hand side. Yeah. Getting more positive. Iron's going from 0 to plus 2. Exactly. So you better put the iron half reaction over here. Okay. Let's see. Consider this voltaic cell. They want us to write the half reaction and then get the overall cell reaction. Now, if you printed this out and made hard copies, notice I made a change here. I changed the nickel to a plus 3. The cadmium is still a plus 2. So first we want to write the half reactions and then get the overall cell reaction. So to me, the trick to doing this is when you write those half reactions, line those arrows up. So when you add things up to get the overall cell reaction, it's a lot easier. when you add the half reactions, you got to make sure what cancel? The electrons. Exactly. So figure out what the two half reactions are. Make sure they're balanced. Add them up and get the overall cell reaction. Then they want you to make a sketch of that whole thing. We're not sure what. Yeah. Yeah. So this guy has to go to him. So keep your reactants as reactants, products as products. So this goes to him, he goes to him. Well, this one, yeah, you flip this one around. This goes to that.
Oh, okay. But how do I cancel these?
You're going to have to multiply 1 by 2, the other one by 3, I think. Right? When you started this out, it should have looked something like this, right? Make sure you write the reactants as reactants, products as products. And then you got to balance those half reactions. And if you add things up, electrons aren't going to cancel. Right? So the common, what's the word for that? Common factor or something? It'd be 6. That'd be the easiest, the lowest number you could use. So I end up with 3 cadmiums. Two of those nickel ions goes to 3 of those cadmium ions and 2 nickel. Right? Now, which half reaction, Mallory, did you put on your left-hand cell there? The CD. In fact, you really don't have to think about it too much because he's on the left-hand side. I mean, you just copy what the shorthand notation told you to do. So it has to be the cadmium. Okay? The nickel one's got to be on, right? So the cadmium's in here. Draw the electron flow, all right? Label your nickel plus 3. Which one did you label as the anode?
CD.
Yeah, the CD. Okay, anode should be on the left-hand side. Okay. Let's knock out this last one, then we. 1952. A voltaic cell has an iron rod in 0.3 molar iron 3 chloride for the cathode, a zinc rod in 0.2 molar zinc sulfate for the anode. The half cells are connected by a salt bridge. Write a notation for this cell. So they want the shorthand notation, right? Or do they want you to draw it out? I think the shorthand notation too, because they use the word notation. It's not all that clear, but I would do the shorthand. So you can figure out which one goes on the left-hand side. Now, you could get by probably with just identifying iron 3 and iron solid, but it's not really necessary. You could write the whole formula for iron 3 chloride if you wanted. What's the formula for iron 3 chloride? FeCl3. Is he right? Yeah, because iron has to be a +3, chloride's a -1. Transpose the charges, you got it. How about the zinc sulfate? What's the formula for it? Is that right? Because zinc is a +2, sulfate is a -2. Yeah, there you go. So there's some strong hints. Right? Which one do you put in the left-hand side? Sulfate. Okay. So which do you write first? You write the zinc rod first, or do you write the zinc sulfate first? It has to be oxidized, so you have to write that solid first, right? If you're not sure, right, it has to be +2. So you could, I see two ways of doing this. You could write the zinc solid and then the zinc +2, if you could really, and it's, what is it, 0.2 molar? Yeah. Or you could write it as a zinc solid and a 0.2 molar, and write the, right? I think either one works, but you have to write that zinc solid first, and you have to have a vertical line between the two compounds. Okay. And then the other one, 0.3 molar iron 3 chloride. So now which one do you write first? The iron 3 chloride, because it has to get reduced. So you write the 0.3 molar. Easier to write it this way, because then it's so much easier to see, right, Fe +3 is getting reduced to Fe solid. It's a lot easier to see than this one. But either way works, right? They're both exactly correct. Okay. So lab this week is lab number 28. Next week is lab 32. Come by if you have some questions. Probably on Friday, if I can get everything straight.